It's my pleasure to introduce Jamie to you, who is going to talk about the optimal redistricting in Virginia. Looking forward to your presentation.
Hey everybody, I'm Jamie and I have the pleasure of working with all of these people with redistricting analytics at Virginia Tech. I'm going to talk about a few different techniques we're working on for redistricting. So in 2018, there was a court case, Bethune-Hill, where the courts struck down a political district map in Southeast Virginia because it was deemed an unconstitutional racial gerrymander. So there was an underrepresentation of African-American citizens within that region. The Supreme Court upheld that ruling in 2019, and a new map was created eventually with more Democratic leaning districts, more African-American influenced districts, and an increased probability that Democrats would win control in the 2019 election, which they did for the first time in a very long time. Gerrymandering is kind of this difficult question. There's not really a good definition of what a gerrymander looks like. I know when I see it is kind of a classic statement concerning that. This is the region in question that was remapped recently. Official districting maps have almost always been hand-drawn. There are some crowdsourced maps, but entirely automated maps have only ever been used in court cases as evidence for or against whether or not a map was an instance of gerrymandering. So those maps only meet kind of very broad guidelines, and they're chosen to support a specific argument. So we're interested in how do we apply optimization techniques to create maps which maximize specific objectives and what the consequences are in terms of other objectives when we do that. And we would like to develop an understanding of what a near optimal map looks like so that we can kind of describe what a good map is. So we create some maps with a hill climbing heuristic, and then we validate those solutions using integer programming, and we're going to cluster the near optimal solutions to hopefully identify some patterns. So we have a couple metrics here. The first one I'm going to talk about is Polsby proper compactness. Compactness is something that a lot of states require in their constitutions for their districts, but there's not really a universal definition for it. Polsby proper is maybe the most common definition. Given the perimeter and the area of a district, its compactness is given by this equation here. We have perimeter squared under the area times 4 pi. So that's going to give a circle a perfectly compact score of 1, and that score varies between 0 and 1 in general. In the Bethune-Hill case, racial representation was the primary failure of that map. So to get a metric for that, we take the total Black voting age citizen population and divide that by the total population of voters in that district and plug it into a CDF, a normal CDF. These parameters were estimated from some data, some election data from 92 to now. So the problem really is an assignment problem. We have to assign each of these nodes, which represent geographical regions, to districts, to exactly one district apiece, such that the populations of each districts are equivalent or within 2%. And our Q is maximized over all those districts, either a Q Polsby proper or a Q representation BVAP. So first, we used hill climbing, simple hill climbing, combination of large and small steps. We borrowed some code from this group here. Our large steps recombined, they totally recombined 2 adjacent districts. Our starting maps are random, and our small steps swap individual blocks between districts. And so in each case, population equality is preserved. And contiguity is preserved. So all the districts have to be contiguous. this is different from some MCMC algorithms in that only improvements are accepted. There's nothing stochastic about whether or not a new map is accepted as incumbent. And larger steps are preferred early and become less preferred as the algorithm continues. So hill climbing, it offers quite a large improvement over the standard in this region and in every region we've looked at. But it doesn't converge to a specific map. So it's kind of difficult to tell exactly how good our best solutions are. So we would like to use IP to evaluate our performance for hill climbing solutions. So we've come up with a few models, but it's important to keep in mind that we care more about upper bounds on the IP rather than actually finding the optimal solution, because that can be more intensive. So this is the Hess model. It's just a simple clustering algorithm, a simple clustering model with some population equality constraints. It's common to use distance as a weight in the objective function, or moment of inertia, or any number of other linear equations. In our case, we don't really care about finding the centroids of our districts, so we use a facility location model, which is considerably smaller. But neither of our metrics are linear, so we're going to have to add a lot to this to get it to function properly. Recall the BVAP, the black representation formula. Notice it has a rational component here, but the populations of each district are constrained to be roughly equivalent, so we can make this approximation to make it linear. Then we also use a piecewise linear function with some SOS2 constraints to approximate the CDF itself. So far, we haven't enforced contiguity in this example because it's rather intensive. And remember, we care more about finding upper bounds to the problem. The Polsby-Popper model is even more complicated. It's also rational. It's also quadratic, and the perimeter estimate requires us to keep track of what blocks are on the border of each district. So we've added a number of constraints. This is for the border. This is for the, and then we use a binary discretization technique for the rational component, because we can't estimate this one because areas are not necessarily equivalent. I can come back and talk about this more if there are questions about it, but for the sake of time, I'm going to move on. Our current model is very large, especially the Polsby-Popper compactness one. It caps out at about 100 blocks of data before it becomes intractable. That's about a county. The BVAP is better, but still caps out at about 500 blocks or so. All of our solutions, though, are promising. Everything we've managed to actually solve validates the hill climbing. So in the case of Montgomery County, which is where Virginia Tech is located, we have the current district map. It's the intersection of 3 different districts. And then we have the hill climbing solution, which is a significant improvement. And it actually managed to find the same solution that the IP found. Notice the numbers are a little different because there's a missing data point here that we never bothered to go back and fix. On the BVAP side, black representation, we have the current model or the current layout. Remember that this is a region that was part of that case that was redrawn to improve BVAP score specifically. So it already has a very good BVAP score. The hill climbing solution has a slightly better one, and our IP solution, which is not contiguous, remember, has this number, 0.51. This is significantly higher than either of these two because it's not contiguous. But remember that we care more about finding good upper bounds than real solutions. So I'm happy with that. That's encouraging. We then use, well, another thing about hill climbing is that it gives, since it doesn't converge to a single map, like I said, we get a lot of different solutions out. So we decided we may as well cluster these and see if we can find any patterns in what good solutions or near optimal solutions look like. This is a cluster of the compactness on the Montgomery County. You can see that the districts kind of rotate around. The optimal one was somewhere between these two, if you remember. This is the BVAP. It doesn't have a spatial component as part of its objective function, so it's even more diverse in terms of what things can look like. Again, the best hill climbing solution we found was somewhere between these two solutions visually. What we want to do next is we would like to improve the performance of IP, maybe by Lagrangian relaxation, maybe by a Bender's style decomposition. We have a few ideas there. Once we get that improved, we'd like to validate more hill climbing solutions. And we'd like to explore some multi-objective hill climbing. So we have a few examples of that. I'm going to leave us with a few maps. Here we have the full region from that court case. This is it's optimized over BVAP by hill climbing. We can see that some of these districts look like classic gerrymandering districts. They're long and stringy, but when we add Polsby proper to it in a multi-objective way, they become much more clean. Here we have the full Virginia. So the hill climbing is capable of running full Virginia in a reasonable amount of time. I don't remember the exact runtime, but we have the same kind of idea. Here's just compactness. Here's just BVAP, and here's both of them. We can see some more stringy gerrymander-looking districts in here. And that's all I have. So if there are any questions, I'd be happy to take them now.